All right, so welcome to chapter 7, which is on organometallic chemistry. Mostly we're going to be focusing on organometallic compounds and reactions of those compounds um, with the D metals. There is organolanthanide and organoactinide chemistry as well with the F metal groups. That's not as rich of an area, hasn't been explored as much, not as much chemical diversity there, so we're not going to have time to dive into that too much, although we'll allude to some of it, okay, through this chapter. So what is organometallic chemistry? Organometallic compounds contain at least one metal carbon bond. That's sort of the definition. It's a very nice definition. And what this ends up boiling down to is that you get a lot of complexes that are sort of mixtures of organic and inorganic chemistry coming together. So you can kind of think of organometallic chemistry as a hybrid between organic chemistry and inorganic chemistry. So because you have a lot of organic type ligands, you can see like these cyclopentadienyl ligands, that's an aromatic group on there. You know, clearly that by itself without the cobalt coordinated to it would be considered, you know, a pure organic compound, just carbon and hydrogen, C5H5 minus. The first organometallic compound was an ethylene complex of platinum discovered in 1827. And so even in the 19th century, people knew that they were making mixtures of compounds that have mixtures of carbon with metals, and that these had unique properties. So they're starting to come up with some of these ideas that, you know, there's probably something special with these, and honing in on this idea of metal carbon bonds even way back then. So iron pentacarbonyl would be an example of an organometallic compound because you see a metal carbon bond. This one called cobaltocene with, like I said, the cyclopentadienyl ligands is a organometallic compound because you have a metal carbon bond. Something that wouldn't be considered an organometallic would be something like this cobalt complex, which, yes, it contains carbon, okay, and it contains a metal, cobalt, but there's no cobalt carbon bonds. It's bonded through a nitrogen. So we would call that more of a classical coordination complex, like we went over in chapters 5 and 6, and not an organometallic compound. A little bit of organometallic nomenclature. By this point, I think you know that I'm not huge on nomenclature, but you know, you'll see this in the literature, and so it's just useful for you to recognize, oh yeah, I remember this eta notation means something. Let me go look that up to refresh my memory. So this is called, has to do with hapticity, or it's called the eta notation. It means that there are n-adjacent ligands bonded to a metal center. So cyclopentadienyl ligand is a great example. Most common bonding form is eta 5. And so that means, you know, you have this delocalized bonding where technically it's 5 coordinate to a metal center. And, you know, there's some molecular orbitals of the cyclopentadienyl ligand that we'll talk about that allow for this bonding to occur. But it's delocalized, right, over these 5 carbon atoms, essentially. Contrast that with an eta 3 connectivity where, you know, you're going to have a free double bond and only 3 of the carbons are really involved in bonding, okay? Or you can have eta 1. All of these are known, okay? Complexes with all these different connectivities can be made. Where in this case, you know, you're only dealing with the connection of 1 carbon. So you only have one atom making up that bond. It's very localized. You can also use this common nomenclature. Sometimes you get more complicated ligands. This is, what would this be? Cyclooctadiene, okay? And you can see it's eta 2, eta 2. It's delocalized across 2 carbon centers, okay, but in 2 spots. So we indicate each of those 2 spots. The eta 2 means it's delocalized across 2, but then we have a comma, so it's delocalized eta 2 here, and it's eta 2 there. Kappa notation. Kappa notation means that, so you use this kappa n, it means that there are n atoms of an element, okay, bonded to a metal. Usually they're not adjacent to one another. We saw this kappa notation when we're talking about polydentate ligands that have a different type of atom, like a nitrogen versus an oxygen that can bind. And so sometimes we say kappa N versus kappa O. Here is now kappa with a number and an atom. So kappa 2O with this trioxanonane ligand. Okay, so that's telling us, hey, look, we're going to have 2 of the oxygens binding to the metal center versus the kappa 3 isomer, right, would have 3, okay, oxygens binding to the metal center. And mu notation means that there's bridging going on. So you could have mu2, this sulfur is bridged between 2 different metal centers now, or you could have mu3. This is, you can have higher mu's and they get increasingly rare, but mu3 and mu2 are the most common. Mu2 by far the most common. Lots of different elements can do mu2 bridging, like we talked about it when we're talking about inner sphere electron transfer, right? Chloride ligands. So anyway, this would be mu3. Common organometallic ligands, there's many. We know organic chemistry is very, very diverse. And so here is carbon monoxide is, you know, although by itself is usually considered inorganic, it does make metal carbon bonds. So it's organometallic in nature. We call this carbonyl when we're talking about it in terms of the ligand. Alkyls, alkenols, alkynyls, aryls, right? All of these are possible. Alkenes versus alkynes. These are going to be eta2. These are all eta1. So if I say alkynyl versus alkynes, you know, alkynyl would be a triple bond with a carbon like that, eta1, and just an alkyne is just a neutral. So it'd be negatively 1 charged, okay, with this ligand because you remove the hydrogen. This is just neutral type of alkenyl bond, okay? So that's sort of the difference there. But, you know, the best way really with nomenclature, as you can see in inorganic chemistry, it can get quite complicated. The best way is just to draw the structure, right? And if you can draw the structure, then who cares really about all these crazy names, right? You can have conjugated polyenes, right? Benzene, linear forms that obviously will have delocalization and a lot of resonance structures. You can have anionic conjugated polyenes. So the allyl group is the most simple of these, where you have a resonance structure. This is an anion of the allyl group that has a resonance structure. So that double bond is delocalized across the 3 carbon centers. Or like we talked about, the cyclopentadienyl ligand. We'll get into more specifics of all these later. And then you have ones that aren't technically organometallic, but have very similar bonding to carbonyl and some of these other compounds. So we put them in the same group. The phosphines with various alkyl groups, wide diversity there. That has bonding very similar to carbonyl, as we'll see, and also hydride or just neutral hydrogen. So these are just some of the few that we'll talk about. We'll talk about more than this, but these are probably the most common. Organometallic complexes have, in general, some pretty big differences to classical coordination complexes, okay? And so the way to think about this is that, you know, coordination complexes have a great deal of ionic bonding. They're predominantly described by ionic bonding, whereas, so they have charge, right? Whereas organometallics generally are more neutral complexes, lower oxidation states, generally speaking, okay? And so as a result, organometallic compounds tend to be very soluble in organic solvents, right? Because they're more neutral. They have more organic, greasy groups on there, more hydrophobic groups. Coordination complexes, since they're ionic, tend to be soluble in water and not so much in organics. The melting points also follow what you expect. You know, ionic compounds like sodium chloride have a very high melting point. So most of the time, the coordination complexes are going to be solid. Organometallic compounds are going to be compounds that are solids that might sublime very easily, or like ferrocene is an example. That's an iron complex of a cyclopentadienyl bis cyclopentadienyl ligand. Very common organometallic complex that can be sublimed very easily to purify it. But you know, they're also, that means, or they could be liquids or solids with low melting points or sublimation points, okay, versus coordination complexes. All right, so in the next videos, basically what we're going to do is we're just going to take a survey. This is kind of a survey chapter of the different ligands in organometallic chemistry, and we'll look at their bonding and some of the properties of their compounds and make connections and look at trends and things like that.